Yeah, hi all. My name is Stefan Schiller. I have a software development background, but later switched to offensive IT security, specifically red teaming. Last year, I joined Sonar's research and development team as a vulnerability researcher. You may know our company for products like Sonar Cube or Sonar Cloud, which help developers to write clean code. One important aspect of clean code is security, which is the domain of our team. This team consists of 4 vulnerability researchers and 1 part-time student, and we try to discover vulnerabilities in popular open source software and use knowledge obtained through our findings to sharpen the engine of our product. In the past 2 years, we've discovered more than 150 critical vulnerabilities and also gained some other achievements. So what can you expect from this talk? At first, only a very short introduction, as I want to show you some bits and bytes as soon as possible. And these bits and bytes are related to 2 major challenges software is facing nowadays: technological variety on the one hand and parallelism on the other hand. Our case study will be Apache Guacamole, which is a remote desktop gateway commonly deployed in enterprise environments. This case study is an interesting example of the hazards related to both of these challenges and results in a parser differential on the one hand and a use after free vulnerability on the other hand. So before we dive in, a quick shout out to this prior research related to Apache Guacamole. The Checkpoint research team published a great article in 2020 covering a nice RCE chain in Guacamole. No worries if you are already familiar with all the details. As we will see in a second, the attack vector they chose differs from what we will be covering. So let's dive in and smash some avocados. As I said, Guacamole is a remote desktop gateway. From a user's perspective, it's very simple. You access the external web interface, you enter your credentials, and you're automatically connected to your configured internal host. You can access this host like a virtual machine fully from the browser. Because of the simplicity of the solution, it's utilized for many different use cases in enterprise environments. It can be used by remote employees to access computers in their company. It can be used for bring your own device deployments to safely access computer resources from a personal device. It is used in popular browser installations, and it can be used for server administration and can be integrated into cloud platforms. So what is happening behind the scenes of this handy solution? Guacamole provides a web interface which is accessed by the browser via HTTP and WebSockets. Guacamole then connects to the configured host via the corresponding protocol. This can be RDP, SSH, or VNC. Once the connection to the host is established, the user can access this host or an isolated application fully from the browser. From an attacker's point of view, the first question is which attack vector exists. And since Guacamole acts as a gateway, there are basically 2 different approaches. The first option is to attack Guacamole from the internal network. This is what the Checkpoint research article covered. When Guacamole, for example, establishes an RDP connection to the internal host, it acts as an RDP client. And an attacker could deploy a malicious RDP server and potentially exploit vulnerabilities in the RDP client of Guacamole. This requires that the attacker has already compromised the host, which can be accessed via Guacamole. The second option is to attack Guacamole via the web interface. This is especially attractive because the web interface is usually exposed to the internet and is a passage to the internal network. Another aspect is that this attack surface is always exposed, independent of whether a user can fully access a host or Guacamole is integrated into a more restricted solution like browser installations. So that's what we will be looking at. In order to understand what we are facing, let's have a closer look at the architecture of Guacamole itself. Guacamole consists of 2 components, a client and a server. The terms client and server here refer to the Guacamole architecture. So the Guacamole client on the left is actually the externally exposed component. It's written in Java and it provides the web interface. It serves the required client-side JavaScript code, it is responsible for the authentication of the user, and it provides the WebSocket endpoint. Once a connection is established, it basically passes all communication through to the Guacamole server. The Guacamole server on the right is written in Java. This component is usually not externally exposed. In a default setup, it's running on the same machine and listening on localhost only. This component is responsible for making the specific remote connection to the internal host via RDP, SSH, or VNC. All communication between both components is done via the custom Guacamole protocol. So what is this Guacamole protocol? Basically, it's a generic remote desktop protocol. It's an abstraction of the specific protocols RDP, VNC, and SSH. Due to the abstraction, the JavaScript client-side code in the browser does not need to care about these specific protocols and only needs to support the Guacamole protocol. Like for any remote desktop protocol, the user input is, for example, a keyboard stroke or a mouse movement, and the output is the screen display of the internal host. The whole communication is based on single Guacamole instructions. And this is an example of such an instruction to move the mouse. It consists of 3 elements in this case, which are comma separated and terminated by a semicolon. The first element is called the opcode, and all following elements are arguments to this opcode. Each element on its own consists of a decimal integer for its length, followed by a separating period, and the actual value. The length of this value is denoted by the decimal integer in front of it. So in this case, this instruction is sent by the client to set the mouse position to the provided x and y coordinates. In order to send this instruction, the connection to the internal host must be established first, of course. For this purpose, the Guacamole client and the server perform a handshake. During this phase, the client tells the server how to set up the connection to the internal host. At first, the client sends a select instruction to inform the server which remote protocol to use. So in this case, RDP. Then the client sends a few other instructions, followed by this image instruction. This tells the server which image types the user's browser supports. At the very last of the handshake, the client sends the connect instruction. This instruction contains all information required to make the RDP connection. So, for example, the IP address of the internal host, the port of the RDP service, and the credentials to use for the RDP connection. Once the server receives this instruction, it actually establishes the RDP connection to the internal host. At this point, the connection is established, and the RDP host can transmit its display data, which is forwarded to the Guacamole client via this blob instruction. Now the user can move the mouse, which is forwarded to the Guacamole server via this mouse instruction. The server translates this to the corresponding message and sends it to the internal host. From an attacker's point of view, we can already make some interesting observations. The first observation is related to the handshake. The supported image types sent from the client to the server are taken from this query parameter sent by the browser. This is the only value a low-privileged user can influence during the handshake. All other values are taken from the configuration within the database. Another thing which really surprised me is this excerpt from the protocol specification. It states that the length field of a Guacamole instruction is not a byte length. Instead, it denotes the number of UTF-8 encoded Unicode characters. So from an attacker's point of view, this promises encoding issues which have already proven to be security relevant in the past. And in this case, this is specifically interesting because of the language difference. The Guacamole client is written in Java and the Guacamole server is written in C. So both of these components need to handle the encoding the same way. And this leads us to one of the major challenges software is facing nowadays: technological variety. There are mainly 2 crucial aspects. On the one hand, we have a vast landscape of technologies, and on the other hand, everything is heavily connected. The result of this is that there's a lot of communication between very different types of components. If these components even slightly disagree about a certain specific of their communication, this can have a devastating impact. Guacamole is a great example of this challenge because it employs 2 different programming languages in a single project. We already figured out that the Java component is responsible for creating and forwarding the Guacamole instructions originating from the user's side. The C component consumes these instructions and evaluates them. So we are particularly interested in how Java creates instructions and how C parses them. On the Java side, the instruction creation is pretty unspectacular. Java's native string class supports Unicodes, so the length method is used to set the value of the length field, and all other values are appended accordingly. So there doesn't seem to be much potential for any bugs here. On the C side, the instruction parsing looks more promising. This is just a little excerpt of the responsible code. The string value of the length field, which consists of a variable amount of digits, needs to be converted to an integer. And for the value, the UTF-8 byte length needs to be considered to determine how much bytes make up one Unicode character. So I thought, come on, there's really a good chance that this does not fit the Java implementation. There must definitely be something wrong with the C code. So in order to determine any inconsistencies between both components, I set up a small and dumb fuzzing environment. At first, we feed some random input to the Java part. Then we generate an image instruction with the input as an argument and send it to the C part. The C part consumes and passes the instruction. And after this, we check if the C parser just crashed or if its internal state is inconsistent. All of this just uses the existing source code, only with a small harness. Yeah, and actually, it didn't take long. This simple setup dumped an interesting input. This is what the dumped input looked like. It begins with the opcode, the image instruction, followed by the argument with the generated input data. These green bytes were randomly generated by the fuzzer, and the surrounding bytes were added by the Java code. Okay, so what did the C parser mess up here? I already mentioned that it needs to determine the UTF-8 byte length to correctly calculate the amount of Unicode characters. And in this case, the most significant bits of the first byte determine that this is a 4-byte UTF-8 sequence. Thus, the following 3 bytes are taken into account, and the result is this CJK Unicode character. Probably some of you know what the meaning of this character is. I had no clue. But what bothered me even more is that I had also no clue why the length field for the single character was populated with a 2. I mean, the C parser ended up in an inconsistent state because another Unicode character was expected, which is correct according to the spec. So maybe we were wrong in suspecting C. Is Java the one to blame here? Let's do some very basic tests. Java agrees that a single A character has a length of 1. Java also doesn't seem to have a problem with this Greek beta character and also agrees that its length is 1. For more fancy characters like this victory hand, Java still agrees that its length is 1. But if we insert our CJK Unicode character, Java suddenly assumes that this character has a length of 2. How does this make sense? And wait, we've been talking about UTF-8 the whole time. Doesn't Java use a UTF-16 encoding? Yes and no, actually. In Java 9, the concept of compact strings was introduced, which dynamically encodes a string internally with Latin 1 or UTF-16. So for a simple A character, which is encoded as a 1-byte sequence hex for 1, in UTF-8, Java also stores this character internally with a single byte because it can be encoded with Latin 1. To keep track of the internal encoding, the string object has a private member called coder. For Latin 1 in this case, the value of coder is set to 0. For a UTF-8 sequence, which cannot be represented with Latin 1, like this Greek beta character, the coder value is set to 1 for UTF-16. This means that the initial UTF-8 sequence is now converted to UTF-16, and the results, which are 2 bytes, are stored internally. So now we are aware of how Java internally stores a string. But how is the length of such a string determined? Actually, very, very easy. This is the internal Java implementation of the string length method. The length of the internal byte array is right-shifted by the coder value and the result is returned. So for a simple A character, which is encoded in Latin 1, the coder value is 0. Because of this, the shift doesn't change the value and the length is just 1. For the UTF-16 encoded Greek beta character, the coder value is 1. This means that the amount of bytes stored in the internal byte array is effectively divided by 2. Thus, the resulting length is also 1. This also works fine for 3-byte UTF-8 sequences like this victory hand. Since it is stored as 2 bytes in UTF-16, its length is also correctly calculated to be 1. So this simple approach is used to calculate the string length dependent on the different internal encodings. Now back to our CJK Unicode character. Java, we've already seen that this character is encoded with 4 bytes in UTF-8. The question is now, how are these bytes converted to UTF-16? And here we are actually getting to the problem. The 2 bytes of a UTF-16 character are enough to map the 1, 2, and 3 byte sequences of UTF-8. But it's not sufficient to map the 4 byte sequences. These sequences are mapped to a UTF-16 surrogate pair. A surrogate pair consists of a high surrogate and a low surrogate pair, low surrogate, which are certain code units specifically reserved for this purpose. Thus, the internal byte array contains 4 bytes for the CJK Unicode character, 2 bytes for the high surrogate, and 2 bytes for the low surrogate. When the character count is calculated, the size of the byte array, which is 4, is shifted right by 1, which results in 2. This 2 is inserted into the guacamole instruction, followed by the original UTF-8 4-byte sequence, which encodes the single CJK Unicode character. Thus, the cparser fails because it expects yet another character. So, what the heck? The Java strings length method is broken? But no, of course it's not, or at least it behaves according to the specification, which clearly states that it returns the number of Unicode code units and not code points. And in this case, this little difference introduces a parser differential between the Java client and the C server. The vulnerability is triggered by UTF-8 sequences that consist of 4 bytes, like this bug Unicode character. Java seems to be more male and tends to exaggerate a little bit regarding sizes, while C is more rational about this. So how can this little difference be exploited? We've already figured out that the query parameter for the supported image types is inserted into the guacamole image instruction sent during the handshake. The query parameter can also be set multiple times to define more than just one image type. All of them are inserted as an argument to the image instruction. What we would like to achieve is to break out of the green value field and inject a whole new query. In order to do so, we can just send a horde of bugs. We set the first query parameter to the 4 UTF-8 encoded bugs, and in the second one we insert an additional instruction which consists of a semicolon followed by the digit 8, a dot, and the string injected. The guacamole client then sends this byte sequence to the guacamole server during the handshake. It begins with the opcode, which is image, followed by the two arguments, the 4 bugs, which Java assumes to have a length of 8, and the additionally injected string. When the guacamole server receives this byte sequence, it's unaware of its structure, so it starts to parse it. The length of the first element is read, which is 5. Thus, the parser wants to consume 5 Unicode characters for the value field. The first, the second, the third, the fourth, the fifth, and now 5 characters were read, and the opcode is complete. Next, the length of the following element is read, which is 8. So the parser starts to read the first bug, the second, the third, and the fourth. But at this point, only 4 of 8 Unicode characters were consumed. So the separating comma is also consumed, the first digit of the length field is consumed, also the second digit, and also the separating dot is also consumed. Now the argument is finished and the parser encounters a semicolon. This means that the image instruction is complete. Thus the parser continues to read the next instruction. Its length is 8, so 8 Unicode characters needs to be consumed. 1, 2, 3, 4, 5, 6, 7, and 8, and the instruction is complete. The string we injected became a whole new instruction. So with this technique, we can inject any additional instruction during the handshake. The instruction we inject is placed right after the image instruction, which is sent during the handshake before the connect instruction. This means that we can inject a connect instruction, which is inserted before the legit connect instruction. This makes the guacamole server ignore the second, actually legit connect instruction, and instead connects to any host we would like to. Cool. Now what? Let's start by exfiltrating some data. The connect instruction sent by the guacamole client contains sensitive items like the credentials used to make the connection, optional passwords and private keys for shared drives, and gateway credentials. All of these are inserted as an argument to the connect instruction. Since our fake connect instruction is inserted before the legit connect instructions, the legit instruction is not only ignored, but it also directly follows our data. This means that we can set the length value of one of our settings to a value bigger than the actual setting. This way, the guacamole server assumes that all data following is the value of this setting. This also includes the second legit connect instructions with all sensitive items, which is now not an instruction anymore, but a simple value of one of our settings. And as we cannot know the length of the legit connect instruction in advance, we might miss the correct boundary as shown by the red arrow at the bottom. In this case, we ended up right in between a false value. But this is not a problem. We just slightly adjust the injected length until we hit the correct boundary. And at this point, we successfully hit this correct boundary. The specific setting of our connect instruction, which is now populated with the legit connect instruction, is called load balance info. We chose this setting because it's sent to the RDP server as a routing token during the initial protocol negotiation. Since the routing token is sent at the very beginning of the RDP connection, we don't even need to set up a custom RDP server and dump some internal RDP handshake data. It's just enough to simply set up a TCP listener on the host we specified in the injected connect instruction, and the Guacamole server then tries to establish an RDP connection to our server and happily transmits all sensitive data in form of the routing token. So let's see this in action. The script starts a TCP listener and now injects different lengths for length fields for this value. At this point, we hit the correct boundary, as we've shown before with the red arrow, and now the Guacamole server tries to establish an RDP connection to our TCP listener, which is not interested in receiving an RDP connection and only just receives all sensitive data which the server sent in form of this routing token. So with this demo, we've seen that an attacker can leverage a protocol injection to exfiltrate the connection settings. What we can also do is to change all settings in the connect instruction. And one feature which can be enabled by this setting is the RDP drive redirection. When instructed to do so, Guacamole can map a configured share to the RDP connection. This share can be accessed from the browser via a dedicated file browser. The problem is that the shared folder is also one setting of the connect instruction. This means that an attacker can leverage injection to define the Guacamole server's root as the shared drive. This allows the attacker to leak any world-readable file on the server. Writing is not possible by default because the Guacamole server, the Guacamole user is very restricted. Nevertheless, this can still be used to leak valuable information like the memory layout of the Guacamole process by reading the proc self-maps file. This information could be very useful when exploiting a memory corruption vulnerability. And this leads us to another major challenge not only Guacamole is facing: parallelism. Doing things simultaneously on its own is not really a problem. If each worker is working on a self-contained task, which is independent from another worker's task, there are no issues with concurrencies. The challenges arise when the same resource needs to be accessed simultaneously. So how much workers does Guacamole employ? When a user connects to the Guacamole server, the main process forks a new child process. When another user connects, a new child process is forked. When a third user connects, another child process is forked. This is done for every new connection. And each of these child processes is responsible for handling the user connection, initiating and maintaining the connection to the internal host, communicating with the parent process, and so forth. All of this needs to be done simultaneously. This means there are a lot of threads. These are just a few of them for each forked child process. So I decided to spend some time looking for concurrency issues. In general, everything seemed pretty solid. All threads are loosely coupled, and mutexes and log handlers are used to ensure an exclusive access to shared resources. But the following feature was very interesting: the audio input feature. This feature allows the user to transmit audio data from a locally attached microphone to the Guacamole server, which is then forwarded to the RDP host. Let's have a look at the related RDP connection flow. Mainly, there are three threads involved here: the input thread, the user thread, and the RDP client thread. The user thread handles the initial connect instruction and allocates two data structures, one for the socket and one for the user. And the user holds a pointer to the socket allocated before. After this, the RDP connection can be initiated, which is done by the RDP client thread. Since audio input is enabled, this thread allocates an additional audio buffer, which holds a pointer to the user. So now there's a pointer chain from the audio buffer to the user to the socket. At this point, all data structures are created, and the RDP client thread establishes the RDP connection to the internal host. If the user now speaks into their microphone, the input thread receives an audio instruction, which is translated to the corresponding RDP audio message and transmitted to the RDP host. Now, let's imagine that after submitting some audio data, the user decides to disable remote audio on the RDP host by selecting this checkbox. This makes the RDP host send an audio input close message, which is handled by the RDP client thread. The RDP client thread acknowledges this message by calling the audio buffer ACK function. This function only has access to the message in the audio buffer. So in order to send the acknowledgement message, it needs to retrieve the socket. Thus, it traverses the pointer chain from the audio buffer to the user to the socket. And the first function being called then on the socket is its lock handler function. So what could possibly go wrong? We are at the point where the RDP connection is established and the user already spoke into their microphone to transmit some audio data. Now the user decides to disconnect from the session. This tears down the user thread, which frees the memory allocated for the socket and the user. The RDP client thread responsible for handling the RDP connection is still running though, waiting for messages from the RDP server. So if the RDP server now sends a message to close the audio channel, the RDP client thread tries to send the acknowledgement message. Thus it accesses the user point in the audio buffer, which is already a dangling pointer. So if the user disconnects first and then the RDP host closes the audio input, we've got the classical use after free vulnerability. So far, this is only theoretical. But can we actually trigger the vulnerability? And here, our first vulnerability comes into play. Since we can make the guacamole server connect to any RDP host, we control this host. Thus, we can make the RDP host close the audio input at the right time, just after the user is disconnected from the guacamole server. So my first thought was, okay, I need to compile and set up a custom RDP server, then figure out how to send the audio input close message, and then synchronize the RDP server with my user connection and send the message at the right time. So I already scheduled a few hours for this in my mind and started to set up a basic XRDP server. But then my expression turned into something like this. I noticed that it just works. I only need to establish a connection with audio input enabled, send some audio data, and then disconnect from the session. The use after free vulnerability is triggered with a 10 out of 10 reliability without any modification of the XRDP server. I then figured out that the reason for this is that the XRDP server explicitly closes the audio input channel before the connection is terminated, which is sufficient to trigger the vulnerability. The Windows RDP server, on the other hand, doesn't do this. So to trigger the vulnerability by accident, you would need to have a connection with audio input enabled in XRDP server, then actually transmit some audio data and explicitly disconnect from the session. So now that we can reliably trigger the vulnerability, we can get to the fun part and develop an exploit. Let's start by having a look at how such a use after free vulnerability is usually exploited. Once the user disconnects, the socket and the user and socket are freed. At this point, we have two dangling pointers. The first one is the user pointer in the audio buffer, and the second one is the socket pointer of the already freed user. So the most straightforward approach is to reallocate the freed socket and populate the lock handler function with some address we want to call. Once the RDP server closes the audio channel, the user pointer in the audio buffer is referenced, the socket pointer in the user is referenced, and our lock handler is called. So theoretically, very easy. The lock handler function pointer here comes in very handy. But here is the first challenge. The chunks are freed right before the thread ends its execution. So it's not possible to do any reallocation in the thread. The user connection is just closed. We could make an allocation from the RDP connection, which is handled by the RDP client thread and is still alive. But the problem here is that since this is another thread, it's also attached to a different arena. Every allocation we make is served from this arena. We are not able to reallocate the freed socket residing in the other arena. So this classical reallocation approach doesn't seem to work. Thus, we need to come up with something else. And one interesting approach is to exploit the use after free vulnerability without any reallocation by leveraging the glibc's heap internals. How does this look like? The socket data structure is freed first. When a chunk like this is freed, there are basically three possibilities. The first, the chunk is put into a T-cache bin. The second, the chunk is put into a bin of its arena. And the third, the chunk is merged with the surrounding chunks. Because of its size, the socket is suitable for the hex80 T-cache bin. Thus, when it's placed here, the head pointer of this T-cache bin is updated to reference the now free chunk. Next, the user is freed. Its size is hex 130 bytes, and the corresponding T-cache bin is also empty, so it would be added to this bin. But let's have a closer look at what actually happens here. We are particularly interested in the socket pointer of the socket pointer of the user. This pointer is located at offset 8, as shown on the top here, and it references the socket. Now, when the user is freed, it becomes a chunk in the T-cache bin. Thus, the first bytes are populated with the forward pointer of the singly linked list. But the next 8 bytes, are also populated with the T-cache key. Thus, the socket pointer is overwritten and is now corrupted. So even if we could control the lock handler in the socket is just not referenced anymore. So this feels pretty much like a dead end. Fortunately, we can prevent that the user ends up in the T-cache bin with some preparation beforehand. Since every T-cache bin is by default limited to 7 entries, we make the application allocate and free 7 chunks with this size before disconnecting. This exhausts the hex 130 T-cache bin, and thus the user cannot be put here. Due to the size of the user, it's also not suitable for fast bin and ends up in the unsorted bin of its arena. Again, let's have a closer look at what exactly is happening here. At first, the user is not freed and holds a pointer to the socket at offset 8. Once the user is freed then, it's now put into the unsorted bin. Because this bin is doubly linked, a backward pointer is inserted at offset 8. This again overrides the socket pointer, but now the socket pointer is a valid pointer which references the unsorted bin in its arena. The problem is that we cannot directly control the memory it's referencing. We would like to place a valid socket here where we control the lock handler. But this memory in the arena only holds pointers to heap chunks. So if one of these were interpreted as a function pointer, this would cause an immediate segmentation fault since heap chunks are marked as non-executable. But if we could free another chunk to the unsorted bin, it would be placed at the head of the doubly linked list. Thus, the backward pointer of our freed user chunk would point to this free chunk. So the question is, how can we free another chunk after the user is freed? And as you may remember, there's actually another free call right before the thread ends its execution. But due to the size, this chunk is placed in the T-cache bin of fast bin. So the thread ends its execution and it's game over. But then I was wondering, since the thread terminates, what's actually happening to its T-cache data structure? And the answer to this can be found in the glibc source code. When a thread is terminated, the function tcache thread shutdown is executed. This function frees all chunks in the Tcache and the Tcache data structure itself back to its arena. And this is done sequentially. So at first, all chunks with a size range of hex 20 up to hex 80 are transferred to the fast bin of the arena. Next, chunks bigger than hex 80 are put into the unsorted bin of the arena. And here is our window of opportunity. The first Tcache bin suitable for the unsorted bin is the size hex 90 Tcache bin. And at that point, when the thread is terminated, this bin is empty by default. So if we would have made the application allocate and free a chunk of the size with hex 90 beforehand, it would have been placed into this TK bin. And this is now the first chunk which is transferred to the unsorted bin during the thread shutdown. Since this chunk is added to the unsorted bin right after the freed user data structure, the backward pointer, which overlaps with the socket pointer, now references this chunk with our data. Thus, we've created a valid data structure. When the audio channel is closed, our fake socket is referenced to the heap metadata backward pointer, and the lock handler is called, which we can control. So both data structures, the user and the socket, still reside within free memory at this point. So this is a use while still being free approach. Once the lock handler is called, we get this, a nice segmentation for it. A few words can be so beautiful, but unfortunately, there's a little problem with this approach. For all of this to work, we crafted some attacker data which is freed to the HEX90 TK bin. We populated this data so that the lock handler pointer, which resides at offset HEX20 this time, is overwritten. The primitive used for this is calling string dub to copy the data from a static buffer to the heap. And string dub is roughly similar to this. At first, the string length is determined, then an appropriate heap chunk is allocated, and at last, the data is copied to this chunk. So in this case, we filled up the data so that the string length would produce a chunk size suitable for the HEX90 TK bin. If we want to populate the lock handler with an actual gadget address, though, this address contains null bytes. So string dub will only take care of the data until the first null byte. This on its own is not a problem because we only have a one-shot gadget anyways. The actual problem, though, is that the size of the allocated chunk is now far less. That means if the chunk is freed, it's put into the HEX40 TK bin instead of the HEX90 TK bin. And when the thread terminates, this TK bin is not transferred to the unsorted bin, but to the fast bin. Unfortunately, this is the only allocation-free primitive reachable from this thread, which makes this instruction pointer control pretty useless. So we need to come up with something else. And let's reconsider the problem with the classical reallocation approach. We have a lot of threads. All of these threads are assigned to different arenas. When the connection is terminated, the user and socket are freed by the user thread and returned to the arena this thread is attached to. In this example, this is arena 4. We could still make allocations, but only from the RDP client thread, which is attached to a different arena 8 in this case. This is where a feature called connection sharing comes into play. Connection sharing means that somebody else can join an existing session. This somebody else doesn't need to be somebody else, in fact. It can also be the same user who initiated the connection. Once a user joins their own connection, no new child process is forked. The existing child process responsible for this connection just creates more threads to handle the shared connection. And there's basically no limit on how often you can join your own connection. This means that we can create a lot of threads. And all of these threads also need an arena. But the amount of arenas is limited. This limit depends on the number of CPU cores. So for 32-bit systems, the limit is twice the number of cores, and on a 64-bit system, it's 8 times the number of cores. So let's assume, for example, we have only one core in a 64-bit system. Thus, we've already reached the limit of 8 arenas. This means for the additionally created threads, the existing arenas are reproposed. With the example shown here, the I/O thread is also assigned to arena 4. The problem is that we cannot control any allocation from this thread. The thread we can control for shared connections is the input thread. Thus, we want this thread to be assigned to arena 4. So what we do is we just join the connection again and create more threads. No hit yet, so let's just join again, and this time we succeeded. The input thread was assigned to the existing arena 4. The allocation primitive available from this thread allows us to also include null bytes. Since it's attached to the same arena as the user thread, we are now able to reallocate the freed socket and user and fully control the instruction pointer this time. Thus, we can finally come to our robbed chain. The exploit conditions are actually very good. The lock handler function pointer is called with the socket itself passed as an argument. One downside of the allocation primitive is that the allocated data is immediately freed again. Although we can make it end up in a fast bin, the first 8 bytes are still messed up by the inserted forward pointer. But we can overcome this with a leave return pivoting gadget. This gadget sets the stack pointer RSP to offset 8, where we can store more gadgets. The first gadget loads the address of system to RCX, and the second gadget offsets RDI to the command string we want to execute and jumps to system. Thus, system is executed with the command string provided as its first argument. So let's also see this in action. We start by setting everything up. We start an HTTP listener to serve our payload. We also start a netcat listener. And now the exploit injects the RDP drive redirection to read the procsafe maps file to leak the libc base address. And now multiple workers join the shared connection. And once the owner disconnects, they start to spray the heap in order to reallocate the socket. And at this point, the socket is reallocated and our ROP chain is triggered, and we receive a reverse shell. At this point, we have code execution on the Guacamole server, but attacked it from the externally exposed Guacamole client. This access can now be used to harvest more credentials, spy on every connection, or just pivot to the host in the internal network. So let's come to a final conclusion. Parallelism has been around for decades, but is still a source of severe security vulnerabilities nowadays. This is not only true for non-memory safe languages like C, but the exploitation part is definitely the most fun for these. In this case, we've seen that it might not be required to reallocate a free chunk to exploit a use after free vulnerability if we can leverage the heap metadata. Of course, this is totally dependent on the specific scenario, but it's definitely a viable option to keep in mind. Furthermore, we've seen that the arena separation can be overcome by spawning a lot of threads. The first vulnerability we've been looking at was all about interoperability. Even tiny inconsistencies in the implementation of different components can break everything. These parser differentials will likely stay the source of very impactful bugs in the next years. So how to find such inconsistencies? Well, at first, there need to be 2 different parsers. And although it's not the hottest hacker approach, reading the specification can be very helpful. If there are some strange specifics like the Unicode lengths we've been seeing, or there are gaps in the specification or certain corner cases, it's probably worth checking if both parsers handle this the same way. And after all, fuzzing is your friend, of course. So thank you very much for attending and listening to my talk. If you're interested in more kind of this content, feel free to follow us on X or Mastodon, and also check out our blog where we regularly release new articles on our vulnerability research. Thank you very much.